Hey everyone, my name's Alistair. I'm here to talk to you about immutable data structures in C++. Before I start, who's enjoying ACCU this year? It's electric, cool. I am aware, of course, it is 4 o'clock. You've been in 3 talks already today. Some of you are probably thinking about the bar, some of you are thinking about the lightning talks. I'll try and keep it a little bit relaxed and a little bit kind of lighthearted. If you have any questions, feel free to interrupt me, it's fine. We're all friends here, just no hard ones, please. The other thing, there's code on the slides. It's what I like to call presentational code. That's a euphemism for a few things. Firstly, it's all gone through a compiler at some point. That point maybe a bit of time ago, maybe got broken during the slides creation process. Sometimes happens. It's also going to be deliberately illustrational. It means I will be a little bit verbose in places to illustrate the concepts. Some code is deliberately, how to put it, bad in places to illustrate some of the concepts. Please don't judge me too critically for it. Before I go into the material, just a quick self-introduction. I am a software engineer team lead at Bloomberg LP. I work in a group called Mars. Mars stands for Multi-Asset Risk System. It's basically Bloomberg's large-scale enterprise risk solution. So we process on the order of 1 to 2 billion calculations every day across multiple asset classes, as the name kind of suggests. And we're just one of many teams doing interesting work at Bloomberg. So if you want to hear more about us, we've got a seat outside at our booth. Feel free to talk to me or any of the other Bloomberg engineers about what life is like at Bloomberg. Another quick kind of, note about the talk before I get into it. I find tech talks tend to fall into about 4 categories usually. The first category are tech talks which are really applicable. You go home and you start using them straight away. I think, for example, if you've never seen standard ranges before, you go home tonight and you can start applying them immediately. The second category are the tech talks where perhaps it's not immediately applicable. You imagine not many of us are probably working in C++23 nowadays, but you can see there's a horizon. You can see in 2 or 3 years you'll be able to use this knowledge, and it's very clear how it'll be helpful for you. The third category are the ones where you go along and think, that's quite interesting, but I'm not sure how it's ever going to apply to my actual life day to day. But maybe in 6 months' time you have a novel problem that comes along, and you think, actually, that tech talk from 6 months ago is the perfect solution, or at least a solution. And it helps you kind of see things in a novel way. And then just for completeness, the fourth kind of tech talk are the ones where you never find them useful at all. I hope I'm not about to give one of those, but you never know. If I'm honest, this is probably going to fall into the third category. While the things I'm looking at today are certainly real problems facing the languages, the solutions are a little bit more blue sky thinking. Though where I think one of the future directions may end up being some of the problems we face today, you may not be able to go home and apply these tomorrow, but I think hopefully you will think of them at some point when you face some kind of novel problem. Cool. So immutability. Immutability, typically something associated with functional programming languages. I think we've been saying for a long time, C++ is becoming more and more functional as the years go by. Who's heard this kind of phrase, C++ is more of a functional language nowadays? It's true, because if you look at the last 20 years, C++ 97, high-level functions in the STL, lifting, all this kind of algorithmic stuff, more associated with functional programming. 11, lambdas, anonymous functions, probably the most typical functional feature. We've got that one now. 17, algebraic data types, optional invariants. Yes, they've been with us for 50 years in the form of unions, but in this kind of more modern format, a pretty new feature. Ranges in C++20. If you saw my talk last year, I was comparing the standard ranges to functions and monads from functional programming. And certainly I think there is some inspiration there from the kind of classic functional world onto this new feature. And then finally, C++23 introduces monadic operators for optional. And interestingly, we're not even scared of the M word anymore. They are just called monads in the documentation. So we've come a very long way. So from some point of view, we're basically there. We have all these cool new functional features. From another point of view, we're actually nowhere near. The kind of key tenet of functional programming really is not around cool sugar like lambdas. It's about data. So in a functional language, at least a pure one like Haskell, you're not allowed to mutate data. That's just not how it works. Same way when you do some maths homework, you don't start mutating the variables in your maths homework. In functional programming, data is immutable. We don't live in that world. We love mutation in our C++ code. That's what makes us who we are, right? We mutate our vectors all the time. And I'm not here today to preach and say we should all become like Haskell. This is not ICFP. We are C++ developers. What I'm here to talk about instead is there are other ways of solving problems. And actually, sometimes some of the stuff from the functional world does help with some of the real challenges C++ is facing today. So let's look at the agenda quickly. So I'm going to start talking about value and reference semantics, something a bit more in the kind of real world of C++. Then I'm going to look at immutable data structures from a different perspective and see how those two things relate to each other. Then we'll look at some implementations. How hard can it be to do this functional stuff in the real world? And then it'll turn out actually quite hard. And we'll look at some of the kind of more modern ideas from modern functional languages. So reference and value semantics, a bit of a kind of, I guess, broad definition. I think the first thing that comes to mind is C++ developers, quite simple, right? If it's got an ampersand or it's got more than one ampersand, it's probably some kind of reference. If it's not got an ampersand, it must be a value, right? It's pretty straightforward. I don't need 10 minutes to talk about this. This is not actually a terrible intuition, but it's not quite the definition I'm going to be using today. So I'm going to be using something from a talk at CPCon 2022 given by Dave Abrahams, who gave a more generic definition of reference and value semantics to be used cross-language, not just in C++. So according to Dave, value semantics basically is based on two properties. The first property is to have value semantics. When you write to a variable, you don't impact any of the other variables. When you have a variable, it also cannot be impacted by writes to other variables. If you have a variable that satisfies these two properties, you have value semantics. This is a slightly narrow definition. I'm not really talking about ownership, which is more of a C++ concept. I'm putting that to the side for now. I'll come back to it a bit later. But for now, we're going to use this as our definition of value semantics. One way this is sometimes treated is, I forget who gives the quote. I think it might be Jana saying, do what the ints do, right? The way you can think about this is if you've got two ints, writing to one int can't influence the other int, right? They just don't work that way, right? They're independent of each other. And that's one way of looking at this. But let's look at some other examples. So I've got two functions here. They're called increment. They are very, very similar. They take in an int, either by value or reference. They increment it, and then they return it. So really, it's only one character of difference, right? Who prefers the code on the left? Who prefers the code on the right? Good. That's what I was hoping for. Why do people prefer the code on the left? And shout something out.
You know what happens.
You know what happens, exactly. So I can read this function, and I can see exactly what it's going to do. If I want to, I can quite safely just rewrite it. I don't know why I'd want to, but I could do ++i instead of I++. I could do some other crazy stuff, and it would, basically be quite safe. I know what the input is, I know what the output is. As long as I can preserve that, I'm more or less okay. If I'm looking at a 3,000-line file, and I've got this increment on the right, and it's incrementing a reference, I don't know why it's doing that. I don't know what the impact of that is. If I change this to, taken by value and remove that side condition, why? What's going to happen? You have no idea, right? And this is kind of one of the really core differences between value and reference semantics. Typically with value semantics, the code is very localized. You can more or less read what's happening without really thinking too hard. With reference semantics, you have these very remote effects where you're implementing the other side of the program. And suddenly you have to read the code very, very carefully and think quite hard before making any changes, because you may blow up something you've never even seen before. So this is arguably a disadvantage, and it's called remote action. There are a few other kind of disadvantages you run into with reference semantics, which you might not do with value semantics. The first one, I can keep this slide up actually. With these two versions of increment, if you have the right-hand function, you actually don't know if I is valid or not. Your caller could have just written a bug in their code and just passed you a null dangling reference, and your function is going to blow itself up. And there's not really anything you can do about that, right? You're basically completely in the hands of your caller to manage the memory for you and give you a valid input. With the left-hand side, that's probably something like, they give you an int which can't be incremented or something. But by and large, it's much harder to run into an invalid input because how hard can it be to pass an int? That's one of the disadvantages. Another one's slightly more involved. So I've got this function on the screen. I'll give you a few seconds to read it. What it's trying to do is append one vector to another vector. So you have one vector called append from. We're just going to iterate over it. We're going to pass everything on to append to. And we're just going to, write out the sizes of append from before and after just to be safe. So append from, you can imagine, the size of append from at the start of the function is 4. For some reason, I've just decided to write it out. Obviously, the size of append from can't change, right, because it's a constant reference. It must stay constant for the length of the function, right? So it's going to be 4 at the end as well, except it's not. Well, how is that possible? Is there a bug in the compiler? It doesn't make sense. How has my append from got bigger, even though it's a const reference? That shouldn't be allowed. And the reason is because the caller's done something slightly unusual, and they've passed vec twice. Honestly, does that look like a bug from the call site? Maybe if you know what the implementation is doing behind the scenes, but actually, it looks more or less reasonable. I'm going to append the same vector to itself twice. Seems more or less okay. The code on the left actually will work in this situation because it's written in a very particular way. So your output will be produced, and it will be 1, 2, 3, 4, 1, 2, 3, 4. So it will work more or less as you'd expect it to. So there's no bug on the screen, but it is a little bit surprising. But who would actually write that for loop like that in real code? Do people typically, write index-based for loops nowadays? Is that a thing we do? No, it's bad practice, right? So a few things that can go wrong. So firstly, even if I write the code like this, so rather than pre-caching size beforehand, I'm going to continuously, query size each time in the for loop. This code is more simple. It looks easier. What's going to happen? It's going to run for a very long time, yeah. Does that look like a bug if you're reading it for the first time? Really, right? I think if you're an amazing code reviewer, you might spot it, but actually that's pretty innocent looking code. But also, as I was saying, we don't do index-based for loops. They're very 70s, right? We don't do that anymore. This is what you'd probably end up writing nowadays. It's very, very innocent looking code. Nothing can go wrong here, right? You run it, it's probably actually undefined behavior, right? Because the iterator is going to get invalidated at some point. Very innocent looking code. Reference semantics can put us into very, very scary places. But this is a bit more of a toy example. I've actually never seen this happen in real code, if I'm honest. It's quite a fun thing to look at. It's a very difficult bug to spot, but not something I've run into in the real world. The next bug is something we've run into in practice, and it has actually caused us some actual production issues. So let's look at this function I've got next. This function is called countEvens. It does what you'd expect. It has a predicate, deciding if a number is even or not, and then it just iterates over its input vector and counts the number of even numbers. I think in practice, you might use std countif because it'd be a little bit more brief, but for the sake of illustration, I've written out the for loop in full. Can anyone see any bugs in this code? I hope there's none, so that should be okay. So you can imagine, I've been working at my desk. I've got this beautiful function to count the number of ints, even numbers in my vector. I go through I do my unit testing. It's all beautiful. I go to beta. There's no problem at all. And then I go to production, and it was all happy. And then a week later, my boss comes to my desk and says, hey, your countEven function has crashed. And I'm very confused by this because my unit test all passed, and there's no obvious bugs in it. And I'm thinking, well, maybe there's a problem with the input reference. Maybe there's a lifetime issue. Maybe someone's passed me a null reference. So I look at the code for a bit. I can't really find anything. The crash stops happening. I think maybe some cosmic radiation just flipped my reference to null. I don't know. I'm just going to forget about this and move on with my life. It's a one-off crash. And then it happens again a week later. And my boss said, okay, no, this is not a one-off crash now. You've got to go and fix it. And I spent a long time looking at this function. I think, how can this function crash? There's no obvious problem with it. What's going on? And so I ask a senior developer in my team, and he says those very scary words. What are the other threads doing? I'm like, well, what other threads? What are they? And so I spent another week debugging the program, and as he said, there's another thread also running at the same time as mine. And for simplification, it looks like this. It's pushing back into a vector, and that's my vector. It's got my vector, and it's pushing back into it. Can then people see what the problem might be now? It's what? Exactly, yeah. So if I get unlucky, well, even if I don't get unlucky, it's going to invalidate the iterator. And then this program's going to crash. Good luck finding that in a unit test. So this is something we ran into in actual production code, and it caused some minor issues because we had some unsafe access to shared data. So this is basically a classic race condition. And sure, you can catch it if you're very, very clever at code review time. Most likely it's going to blow you up in production once and twice, then you'll come up with some way of fixing it with a lock or something. So, not great, and something very unique to reference semantics, sharing code across multiple places at the same time. So there is an easy solution to this. You just use value semantics. So now, I'm just going to take my vector by value. And now no one else can touch my vector because it's mine. I have the only copy of it. It's private to me, and no thread can hurt me. And to be reasonable, provided you pass by value all the way, my crash is now fixed, right? I cannot crash inside my countEvens function. Who thinks this is a good idea? Yes. There is a small downside in that now my count evens function used to be linear in time, but at least constant in space, right? I didn't have a space requirement. Suddenly I've got a linear space requirement to count the number of even numbers for a pretty innocuous looking, function. That's not really very good, right? I think while value semantics clearly does fix the issues we had, we can't go around passing things by value everywhere because we're going to pay a lot more costs. And for completion, it also fixes my issue with append from as well. If I pass append from by value, I can keep passing append to by reference, that's fine. Now I'm no longer going to be updating append from while I'm also pulling from it, and the code will work completely fine. But again, is it reasonable to be passing these things around by value at high cost just to avoid these problems? Probably not, right? Value semantics may solve some problems, but we're writing C++ for a reason. We don't be copying every single vector we're dealing with. And so in practice, I imagine most of us are working with coding standards where we have something like, if you have these user-defined classes or data structures, pass them by reference to save time. And for primitive types, it's okay to pass by value. So there's a partial solution here, but clearly we have some kind of performance bottleneck keeping us from going all the way. To sum up so far, reference semantics, where we normally do things, there are quite a lot of downsides. This action at a distance is confusing. You have lifetime issues. You have aliasing issues. You have race conditions. But while value semantics may fix all of those things, you have a real problem with heavy objects. If you go copying objects everywhere, you're basically defeating the point of using C++ in the first place, right? So I'm going to pause this here for now. The big takeaway really is we would like to be using value semantics to solve the problems above, but in the current state of C++, we can't always justify it for heavy object classes. So taking a slight diversion, I want to talk about immutability now. So I think we have some intuition what immutability is, right? It's the const thing, right? How hard can it be? It's a thing that can't change. C++ is slightly confusing because it has slightly different use of const to other things, but by and large, it's fairly simple. Some of these consts can't change, right? I'm going to look at immutability from a slightly different point of view. I'm going to look at it from the point of view of value and reference semantics. So just to recap the earlier slide, value semantics require two properties. Number one, writing a variable does not impact other variables. Number two, the variable is not impacted by writes to other variables. And now let's look at some code. So I've got a vector, I'm going to call it myvec, and I've got 4 references to my vector. All of these things are const. So my original vector is const, and all my references are also const. So I think quite clearly we can see the vector probably has value semantics, right? It's a value, it can't be impacted by other variables, right? The slightly more interesting argument we can make, what semantics do the references have? I mean, clearly the references can't be written to because they're const, so therefore they can't impact other variables. But in this world, they're also not impacted by writes to other variables, right? So these references actually do have value semantics, at least in my interpretation. There is obviously, as always with C++, there is a caveat. If I take my vec and I const cast it away and I start modifying it, of course I lose my value semantics and all the references, but we're just gonna hand wave that away and say, const casts are bad and you shouldn't do them. But this is quite interesting, right? When I was talking about value semantics before, for heavy objects, the disadvantage was that the copies killed you, right? But if these references have value semantics, I get the benefits of all the safety without paying the heavy cost. But there's always a but, right? So these const references do, I think, have value semantics. Do these const references have value semantics? No, because they can be updated by and changed to myvec. The painful thing about C++ is, if you're just consuming a reference, do you know whether it's this kind of reference, a reference to a const vector, or it's this kind of reference, a reference to a non-const vector? You do not, and that's some of the confusion with const in C++. You don't actually know exactly how const you are, if that makes sense. You don't know if you've got your const to const or const to non-const, which is a little bit annoying, right? So this is where we start going into slightly more creative thinking. What if I cheated a little bit? What if I defined a new vector and I just deleted all the non-const operations? And therefore, I know it's const because it doesn't have any non-const operations in the first place. So I'm going to have a new class, and I'm going to call it const vector. And I'm just going to delete a load of stuff. So no assignment, no updates. What can I really do with it? I can check the size, and I can look at the elements. And that's basically it. And to be honest, it doesn't matter if it's const or non-const because it effectively is always const, right? You can't change it unless you, I don't know, start doing some weird memory manipulation. So I've got a class called const vector. I can use it as my basis, and I can pass const references everywhere. And I've got value semantics. Cool. What's the but here? The challenge is you can't do very much with this thing, right? All you can really do is check the size and check the elements. Of course, you can't update it because that would be a non-const operation. But typically, with this kind of functional data structure, you have the ability to add elements by a pushback. And it looks a bit different to the pushback we're familiar to. So let's have a look at it. So, sorry?
You didn't strike all.
Which one did I miss? Which one?
Let's say operate.
Which one do you want?
Operate the square brackets.
Yes.
Not be,
You are correct, yeah.
and I saw also kind of reserve.
Yes.
So not really const.
Yeah, and I left the non-const iterators in because I couldn't find a nice way to strike them off. But you are right. I was a little bit clunky.
Also data.
It's which one?
Data.
Data, yeah. Where is? Oh, you're right. Yeah. Sorry, I should have been more careful with my strike throughs. You are right. So yes, take the criticism. Imagine everything non-const is stricken off, not the ones I've stricken off. So often these const data structures have some kind of operator like this, which is cool. We'll call pushback for consistency. As I mentioned, you're not allowed to actually modify the actual data structure itself. So typically what this operation will do is take your existing value, add one more value, and then give you a new data structure with the new value, right? This is pretty common in functional languages. You know, if you've got your camels and your Haskells of the world, they will have this kind of append operator, or actually that's the wrong word, cons operator or pushback operator, where it will just add one element and give you a new data structure, right? What is the complexity of that pushback operation? Well, it's not good, I'll tell you that. So that's a linear time update, right? So if I want to get a new data structure, just say I've got a 1, 2, 3, 4, 5, and I want 1, 2, 3, 4, 5, 6. That's a linear time operation. That is extremely expensive. The whole point of this is C++ is to be fast, right? If I'm introducing a new data structure and I want O of n time and space to push back onto it, I've got a bit of a problem there, right? And that does, while it's a step in the right direction, it does kind of poo-poo the idea a little bit. But I was saying a second ago, this pushback thing isn't some crazy thing I've just invented just now. Well, okay, partly is, but it's also something I've taken from other languages. So, as I mentioned, the list structures in, say, a Camel or Haskell will also have this kind of operation of, I've got a data structure, I want to add one more element and get a new data structure. Are all the functional programmers running around with linear time updates? Actually, maybe they are, who knows? But probably not. So let's have a look at some different languages. This is the only slide in the entire presentation of a different functional language. I'll go through it slowly in case people aren't really familiar with a camel, but hopefully it's fairly straightforward. So this is a 3-liner camel program. Line 1 is defining a list object. So in a camel, this kind of square bracket is the list literal. And for whatever reason, they've chosen semicolon as a list separator rather than comma. So list A is a list of values 1, 2, 3. On line 2, I'm going to define a new list called list B. And this kind of double colons thing, you can think of as effectively a push front. So what it's doing is going to create a new list of values 0, 1, 2, 3. And then just for completion, I'm going to append the two lists together. The interesting thing about a camel and other functional programming languages, data structures are always immutable. List A is 1, 2, 3. List A will always be 1, 2, 3 until the end of the universe, or at least until you turn your computer off. It will be 1, 2, 3. No matter what you do to other variables, it will always be 1, 2, 3. So an interesting thing is that a camel is a bit of a special case. It has some reference semantics, but for most functional languages, everything is value semantics. I think a functional programmer may have found the first 15 minutes very confusing because why are we even messing around with this in the first place? Just use value semantics everywhere. So list A is always 1, 2, 3, and list B is 0, 1, 2, 3. And appending them together, you should get 1, 2, 3, 0, 1, 2, 3. And to show the output quickly, this is what we get, right? So you have 1, 2, 3, you have 0, 1, 2, 3, and you have 1, 2, 3, 0, 1, 2, 3. So this is hopefully a fairly simple program. What I'm really interested here is not the kind of simple code itself, but what the language is doing behind the scenes. So let's start looking into at least an imaginary version of the program's memory. So this green thing is list A. It's 1, 2, 3. What's list B going to look like? List B is an independent variable with value 0, 1, 2, 3. If we do it naively, we're going to end up with that, right? And it's going to be a completely different data structure, linear time to create, linear memory to create. I'm going to have to basically redo the whole thing, and my push front has linear complexity. But functional programmers are clever people, and they're going to exploit what I just told you. List A is 1, 2, 3, and list A is always going to be 1, 2, 3. So I've got a 1, 2, 3 in list B. I don't need to go away and make a brand new 1, 2, 3 for myself. I've already got one. So functional programmers are sneaky, and they will optimize by reusing list A as part of list B. This is effectively called structural sharing. So list A is the green one, list B is the yellow bit plus 1, 2, 3. And I've got two completely independent lists from the point of view of the programmer, but behind the scenes, I've effectively got one list with 4 elements, right? This is pretty cool. So I think often when we think about mutability, we think speed and performance, but actually, sometimes you can exploit immutability to save yourself time and memory, which I think is quite neat. So, lists seem to be the answer to our problem. Maybe we just use lists everywhere in our code instead of vectors. Who likes the idea of that? No, didn't think so. What's wrong with lists? Sorry? Yes, well, among many other things, yes. So linked lists have many problems. Obviously, as you mentioned, cache locality is very bad. You're doing all these hops around your memory. Your element access is very slow. You have linear time to access things in the middle of the array, in the middle of the list. And yeah, I mean, those can get smoked by C++ vectors in most circumstances. So to quickly summarize, I have my const vector with O of n time and space updates, pretty bad. My list has O of 1 updates, but it's got O of n element access. And also, even that aside, while pushback and adding to a list are both O of 1 operations for doing vector and list, the vector is going to be much faster purely because of the memory locality. So it's a more performant data structure. So we get part of the way there, but unfortunately, we're still not quite where we want to be. We still haven't got a performant const data structure. So let's take where we are so far. Firstly, const data structures are very hard to write performantly. There's a lot of challenges. We've tried twice, and we've kind of failed. Structural sharing is a technique used by functional languages to optimize. It can make things faster. It's pretty cool. It didn't help us too much here, but it's important to bear in mind. And the big thing, arrays beat linked lists. So a few years ago, this probably would be the end of the presentation, we say it's pretty cool. You know, we get some of the way there, but the technology does not yet exist to get us to the future. Slight exaggeration. But I want to introduce one more data structure, which, while it's not perfect, takes us a lot closer to where we want to be. And it's called a persistent vector. This is something which was introduced into modern functional programming in the early 2010s. I couldn't find a very clear source line for the very first originator, but certainly it was introduced into Clojure and Scala in the early 2010s. And really it was written to keep the parameters of functional programming, value semantics, immutable data structures, without burning yourself to pieces on performance, having some kind of competition with what C++ and other languages can give you with mutability. So it looks a bit like this. You may have a few questions. Firstly, that is a tree, not a vector. What's this guy talking about? And secondly, it looks pretty slow. I've got all this indirection in here. You know, what's going on? So let's look at it in a little bit more detail. So what are we looking at? So you are right, this is a tree, but it's also a vector. So your elements, your vector are along the bottom here, and you have a header pointing to the root. And then your elements are effectively laid out in a tree structure. So this is a vector of length 7. All of these boxes are fixed size arrays. So aside from the top one, which is the header, you define some branching factor at the start of your data structure. For this one, I've chosen 4, mostly because 4 is nice to fit on the slides. In practice, you use a much bigger number. And you basically go down the tree in order to find the elements you want to find. So first question, how do I actually find an element in this tree? So let's say I want to find the 5th element. Unfortunately, zero indexing is very nice for many things, but not for this. It's very confusing in this situation. So the 5th element is this guy, number 6, which is very confusing. This is element 0, that's number 5 is the 6th one. So how do I find the 5th element? So it's actually pretty cool. You use base conversion to figure it out. So this tree has a branching factor of 4. And so what I do is I convert 5 into base 4. And I get this number that looks awfully like 11. I'm not going to call it 11 because that's confusing. But I have this 1, 1, which is 5 in base 4. And then to get to my element, I just traverse the tree, right? So I get to the first one, I pick the oneth, this is confusing, the oneth element, which is number 2, which is confusing. And then again, you pick the second one again. So you can traverse a tree in this way. And by using the index of the thing you're looking for, you just go down the tree. This is, I'm going to pronounce this wrong, this is like a trie, T-R-I-E structure. So this thing's also known as called a vector trie. I'm going to use a bigger one just to prove that wasn't luck. So this is a 3-tier tree. It's in theory, it has a capacity for 64 elements. Some of them are off the side of the screen because I ran out of space. So you have to use your imagination a bit. So I want to find the 38th element of this tree. And I'm going to do a base conversion to base 4. In base 4, 38 is this thing that looks like 212, which I'm not going to call 212. And then I go over here, I say, okay, I want the 3rd element. And then I want the 2nd element, number 1. And then I want the 3rd element again. And my 38th element is a 3. You can count them out if you really want to, but you can just trust me. That is the correct answer. So that's quite cool. I think that's quite a neat algorithm. What's the complexity of looking up an element in this vector? Log n. Yeah, that's pretty cool. So probably nothing mind-blowing there. Looking something up in a tree as log n. This is where the slightly creative maths comes in. So I apologize, but it is important. So logs. I hope we know what logs are. They're quite relevant. Not the logs you put into your hard drive, the logarithms. So on this data structure, many of the operations are logarithmic in the branching factor. Typically, the implementations thing use a branching factor of 32. Log base 32 is often not a very big number. So log base 32 of a billion is about 5. Log base 32 of a trillion is about 8. So you can be a little bit naughty here. You can say, actually, there's log base 32. The biggest it's ever going to be is about 20, right? So you can just say, hey, it's const. This is a little bit informal, and it's a little bit cheating, but this is kind of the kind of fundamental here, is that a lot of your operations actually effectively have const complexity. But it is const with a big overhead. It's not const in the way, popping back to a vector is very, very cheap. It's a big const. But when you have, a trillion things in your vector, you've probably got much bigger problems. But having, 8 operations to do is not so bad. So I have updated it to be O of 1 time and O of 1 time. For those at the back, the O of 1 is in italics to, mention this, a slightly creative use of O of 1. But in theory, you have O of 1 time. So that's kind of neat. But, adding things to a tree or looking up things in a tree is log n. No one's mind is blown. Saying log base 32 of n is 1. A bit cheeky, but again, no one's mind should be blown by this. Let's look at the actually cool thing. So I want to push back onto this tree. I've got a thing of 7 elements. I want to push a 10 back onto it. And afterwards, my tree is going to look like this, right? So I've now got a size of 8, not 7. And I've got a 10 on the end. What's this going to cost me? I mean, if I want to, I can just copy out this entire structure, and then it's linear like I was in the first place. Probably slower because of all this indirection and stuff. But we can reuse what we learned earlier. We're not going to do a naive copy. We're not going to be O of n. We're going to use structural sharing. That red looks really bad at the back. I apologize. Looks much clearer on my screen. Can everyone see it at the back okay? Okay. So rather than copying my entire vector, I can say, actually, between my first vector and my second vector, most stuff's actually the same. So on this slide, the blue vector is the original vector, and the red vector is a new vector, and the green vector can be shared. So when I build my new vector, all I've actually got to do is update 3 of the boxes, whereas previously I was copying all 6 of them. So I'm getting some optimization here, and I'm just sharing things between my old vector and my new vector. For a small vector, this is still very expensive because you have copied an awful lot of things. When you have thousands of things in the vector, and you're copying on the order of 4 or 5 arrays of size 4, or, it's much better. And again, it comes to the cheeky question. What's the complexity of this operation? So you're only going to operate in the height of the tree, which means you're going to be log n again. It's an expensive log n because you're doing a lot of copying, but it is log n. And as we've learned today, log n is 1. So this thing is just as fast as a std vector. So I'm slightly creative with my maths here. This is unfortunately the very disappointing part of the presentation. Unfortunately, I didn't have time beforehand to get all the benchmarks together in order. So I've only got some very rough estimates rather than any proper graphs. Is this thing as fast as a vector, do you think? No. But it's not as slow as you think it would be. I think there has been some more detailed research into this. It's not going to be competitive with the std vector, but for some use cases, you are going to get pretty okay performance, right? It's going to be better than the list. It's going to be okay, right? There's in my afternoons, I'll mention a bit more. So it gets you some of the way there, right? But I think this kind of illustrates kind of the real question. With some very creative thinking, we can have this kind of const data structure which gives us good value semantics. But the std vector is basically unbeatable, right? And at some point, you have to say, actually, do I want value semantics or do I want speed? And that's a trade-off every developer's got to make for their own thing, right? I think one thing I've learned in my career, there usually isn't a perfect solution for both speed and safety. And I think what we're looking at here, in theory, gives you more safety around race conditions, but you are looking at it in the context of decreased performance, right? Let's be open about it. So, just to take away some conclusions then. We live in a multi-threaded and multi-core world. This is going to be the case probably for the rest of our careers unless something very seismic changes. We're maybe using a language from the 70s and 80s, but we live in a multi-threaded world. In that world, the reference semantics in C++ are not always super friendly. They have downsides, there's all these kind of dodgy things, and they're extremely prone to race conditions. Often, there are many presentations saying, reference semantics are bad. You should use value semantics and it solves all the problems. And it kind of does, right? Many of the problems we have were solved by value semantics. It just introduces a whole lot of other problems around performance instead. So there isn't a perfect answer here. As of today, the data structures we have natively in C++ in particular don't work particularly well with value semantics. Copying vectors is extremely expensive and cumbersome. Parsing vectors by reference or by value, sure, it helps you with your race conditions, sure, it helps you with aliasing. You have a lot of other problems on the side. But this isn't a new problem. Value semantics has been the default in functional languages forever. And yes, C++ is probably faster than almost any functional language still. But they've come an awful long way, and they've found new solutions for things. And this persistent vector I've shown, sure, it's not as fast as a real vector, but it's pretty fast. It's come a long way, and this will move further and further. I think if we are going to use value semantics as our actual solution to things, we should be looking into the work other languages are doing, and they could make things a little bit easier for us. A few follow-ons, if people are interested in looking a bit further into this. I skimmed over value and reference semantics very quickly at the start of this talk. There are much better talks on it out there. In particular, Dave Abraham at CPCon 2022 gave an excellent talk on value semantics and why he feels it's the answer to many of the problems the language is facing. I'd recommend anyone who's interested to take a look at that one. And I think it is, well, it's certainly a very useful talk to look at. I've deliberately focused on vectors to keep things narrow. This isn't because vectors are the only thing this has been solved for, but because they're the most simple thing. People have looked at associative containers, maps, sets, etc. You can look at those as well to see where we are. And benchmarking, unfortunately, I didn't have time myself to get my own implementation quite up to scratch, but there's a lot of existing work in this space. In particular, there's a paper from ICFP 2017 about persistent data structures, actually implemented entirely in C++. Crazy, right? So ICFP is the biggest functional programming language conference, and someone presented a C++ paper, very brave. And it did look at some of the benchmark around this. And with some additional performance optimizations, yes, it wasn't as fast as Vector, but it was pretty performant. It outperformed many other kind of standard data structures. So there is already some work in this space. People who are interested can look a bit more into this as well. That takes us to the end of my presentation. Any questions?